This video is an explanation of the reading comprehension passage about asteroids. Now, this could be watched in conjunction with any question about the passage, and of course, each question is discussed in its own video explanation. I will say if you're going to do multiple questions in a row about this passage, I would encourage you to do all the questions first, then watch this video. That way, you'll answer the questions with your own understanding of the passage. This is a long passage, so let's talk about this. Originally, scientists predicted small asteroids to be hard and rocky, as any loose surface material, called regolith, generated by impacts was expected to escape their weak velocity. Aggregate small bodies were not thought to exist because the slightest sustained relative motion would cause them to separate. But observation and computer modeling are proving otherwise. So stop right there. Notice that we're given briefly the original theory. The original theory, and the passage lets us know quite clearly that this original theory has lost a lot of traction, that all the evidence is actually pointing it the other way at this point. But this original theory was that small asteroids were hard and rocky. They were solid rock, and there wasn't much loose material. But, and this is a really strong change in logical direction, but observation and computer modeling are proving otherwise. Most asteroids larger than a kilometer are now believed to be composites of smaller material. Notice that this is the exact opposite of what they originally thought. Those imaged at high resolution show evidence for copious regolith, copious loose surface material, despite the weak gravity. Most of them have one or more extraordinarily large craters, some of which are wider than the mean radius of the whole body. Such colossal impacts would not just gouge out a crater, they would break any monolith body into pieces. All right, stop right there. This is really subtle. What they're saying is that if the asteroid were a monolith, if it were a solid body, a solid single piece of rock, then a colossal impact would shatter it into little pieces. And so the fact that we see these asteroids with these really, really large craters, what that means is they can't be solid bodies. And therefore, they have to be these aggregates of smaller bodies. And so this is a very strong piece of evidence. This is one of the pieces of evidence for this new theory. The fact that many of these asteroids had these large craters. In short, asteroids larger than a kilometer may look like nuggets of hard rock, but are more likely to be aggregate assemblages or even piles of loose rubble so pervasively fragmented that no solid bedrock is left. Second paragraph. The rubble hypothesis, proposed decades ago by scientists, lacked evidence until the planetologist Shoemaker realized that the huge craters on the asteroid Matilda and its low density could only make sense together. A porous body, such as a rubble pile, can withstand a battering much better than an integral object. So again, what we said earlier, that if it were a solid integral monolith, then it would not be able to withstand that impact. But the fact that all these asteroids have these big craters, it means that they must be mostly loose material. It will absorb and dissipate a large fraction of the energy of the impact. The far side might hardly feel a thing. At first, the rubble hypothesis may appear conceptually troublesome. The material strength of an asteroid is nearly zero, and the gravity is so low one is tempted to neglect that too. The truth is, neither strength nor gravity can be ignored. Paltry though it may be, gravity binds a rubble pile together, and anyone who builds sandcastles knows that even loose debris can cohere. The oft-ignored details of motion begin to matter: sliding friction, chemical bonding, damping of kinetic energy, etc. We're just beginning to fathom the subtle interplay of these minuscule forces. So very interesting. The rubble hypothesis may appear conceptually troublesome. And it's troublesome precisely because all the things that we normally ignore, all the tiny forces that we think, oh, that's so tiny we don't have to pay attention to it, here it seems these tiny forces matter. And so that's what's really interesting about this. that all the things that all these scientists were used to ignoring, they can no longer ignore in this particular scenario. And these are things such as material strength, the weak gravity. There's a wonderful analogy here of sandcastles. So the fact that sandcastles cohere even though they're made of loose material, this is not, of course, direct evidence, but it's an analogy for how a loose asteroid holds together. So let's move on to the third paragraph. The size of an asteroid to determine the force, which force dominates. One indication is the observed pattern of asteroidal rotation rates. Some collisions cause asteroids to spin faster, others slow it down. If asteroids are monolithic rocks undergoing random collisions, a graph of their rotation rates should show a bell-shaped distribution with a statistical tail of very fast rotators. If nearly all asteroids are rubble piles, however, this tail would be missing because of any rubble pile spinning faster than once or twice every 3 hours would fly apart. All right, let's quickly diagram this. What they're saying is, suppose we had this graph here, and this would be rotation rate. And this is spinning very fast, this is spinning very slow, and what they're saying is that there would be this bell curve. If they were monoliths, there would just be this bell curve like this. And there'd be some that were moving really slow, a lot would be spinning at kind of an average rate, and then a few would be spinning very fast. Now that's if there were monoliths. But if they're rubble piles, that means that the really fast ones would fly apart. So this tail here would be missing. And so what we'd get is the rest of the bell curve without this extra tail up here. And so this is the tail they're talking about, the tail representing the very, very fast spinning asteroids. Recently, several astronomers discovered that all but 5 observed asteroids obey a strict rotation limit. The exceptions are all smaller than about 150 meters in diameter, with an abrupt cutoff for asteroids larger than 200 meters. The evident conclusion that asteroids larger than 200 meters across are rubble piles agrees with recent computer modeling of collisions. A collision can blast a large asteroid to bits, but those bits will usually be moving slower than their mutual escape velocity, the lowest velocity that a body must have in order to escape the orbit of a planet. Over several hours, the gravity will reassemble all but the fastest pieces into a rubble pile. And so what we have here are 2 kinds of evidence in this last paragraph. Kind of evidence number 1 is that all the asteroids larger than 200 meters, those are the ones that have a strict cutoff or rotation rate. None of them are spinning faster than some upper limit. We don't know what that upper limit is, but that doesn't matter. There's some upper limit and nothing is spinning faster than that. And there's just a couple that are spinning faster than that, but then those are really small ones. And so this certainly suggests that all these larger asteroids are rubble piles. And then computer modeling suggests that what happens if a rubble pile, well, it seems that if it got in a collision, it would just blast to smithereens and it would fall apart. Well, what the computer is suggesting is that for the most part in a collision, it would separate, but then it would come back together. And so this explains how these rubble piles would continue to exist.